very, very close to the point in our lives that we are able to write and name chemical formulas. That is perhaps the biggest thing that you learn in chemistry. In order to do that, we need to be able to know a bit about the periodic table, because the periodic table becomes the most important part for writing chemical formulas. So I'm just going to give you a little bit of an introduction one day. Okay, come January, we'll spend a week on the periodic table, but for now, all we need is about 1 day's worth of information. All right, so today, I want you to be able to identify and describe the various features of the periodic table and identify the properties of metals, nonmetals, and metalloids. Okay? All right, since we're going to be using our best friends, let's get to know him or her a bit better. First of all, where can you find the atomic number? Z. Atomic number. Top. It's the whole number, right? Where do you find the mass number? The sum of protons and neutrons? Bottom. Okay, be careful, because that's really not the mass number. That is the average atomic mass. So that is the average, the weighted average, and we'll find out later on what weighted average means. That is the weighted average of all the isotopes. All right, so here we are. Okay? First thing I want you to do is take out a pencil or pen, just a pencil or pen, not a marker because it'll bleed through, and I want you to make this line a bit darker, the zigzag line. Make it darker. That is the dividing line between the metals and the non-metals. Well, a lot of the nonmetals are gases, but not all. So you're kind of right. There should also be kind of like, you might want to draw a darker line between hydrogen and lithium as well. Hydrogen and lithium. Look up here, hydrogen and lithium. Because really, hydrogen is not a metal. It should not be on the metal side. I'll explain here in a few minutes why. Okay? Some elements have unusual designations, like they have numbers or really unusual names, like unaldecium. Well, that's just a temporary name. The IUPAC is still fighting over who it should be named after. Notice the periodic table is arranged in columns and rows. Who first designed the periodic table? Yes. Dmitri Mendeleev. And we'll learn more about him, thanks to Hank Green. We'll learn more about him later on. What is the name that's given to the vertical columns? The groups or families. Groups or families. What is so special about them? Well, the fact is that pretty much if you're in the same column, then you will have very similar properties. Just like, you know, the Lenores are all the Lenores. Why? They were all, you know, they were all raised the same parents, and they're going to take on a lot of the same characteristics as their parents. The Lenores are the Lenores. Okay, in the same way, the families, all families have similar properties. My family in particular, they're a little strange. All the members of my family are a little strange. Well, that's because the parents are a little strange. All right? Now, why is it that these columns will take on family-type characteristics? You're not mature enough to understand. I'm sorry. No, I won't tell you. I will tell you in January. If you can survive, those of you who are going, oh, I must, you have to survive next 9 weeks, which is the toughest of all the 9 weeks. If you can survive next 9 weeks, you can survive all of chemistry. It's very mathy. Very mathy. You're going to have factor labeling. You're going to have train tracks out the wazoo. There's just lots and lots of train tracks. All right, here's some families, some consistent families. Because some columns you go, well, yeah, no. Some families that are really strong, families that are very similar. First column, and please, you're not allowed to write anything on your periodic table unless I tell you. So this is for your notes. Actually, it should also be on the back of on your worksheet. The worksheet, this worksheet is due tomorrow. Make sure it's done for tomorrow. Alkali, first column. First column is alkali. Alkaline, I think they did that just to confuse you. Alkaline, what's the difference between the alkali metals and the alkaline metals? And Ne, yes, Ne. Okay. No, they're very different. It's more than just the Ne, I guarantee. Halogens is another very consistent family, and this is the 7th or the 17th column. Why, Mr. Rayner, why is it the 7th or the 17th? Believe it or not, there's like 5 or 6 different versions of the periodic table. Some versions of the periodic table include the middle 10 section. You notice there's like a middle 10 section. They include that middle 10 section as different families. Some consider that whole middle section as a family all by itself. So there's only 8 really true families. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay? So this is either the 7th family or the 17th group. Yes? No. All the symbols are the same. The names may be spelled differently. I mean, we've got the same problem with Na and K. Well, yeah, most of the world has even more problems than that, because it's not just Latin, it's also English. So they're all going to use the same symbols. The symbols are international. Their names, I think in Spanish, sodium is sodo. The names are going to be spelled differently, they're going to be pronounced differently, but the symbols are all the same. Good question. Noble gases. I think the noble gases are actually on your periodic table. It says noble gases on there. And all the noble gases pretty much act the same. Horizontal rows are called periods. Periods. They're numbered from 1 to 7. Horizontal rows are called periods. They're numbered from 1 to 7. Yes. Phoebe, check out. I'll have this up this evening. First 2 columns and the last 6 columns are called the representative elements. So that middle section is called the transition metals. The middle section is called the transition metals. If you look carefully, you'll notice that the 14 columns that are below it actually fit into the middle section. It's as if they reached into the middle section, ripped out 14 columns, and threw them down on the bottom, and that's what they did. Actually, it was an Oak Ridger by the name of Glenn Seaboard, who used to live on New York Avenue. He's the one who first suggested, hey, let's do this or else the periodic table is going to get messed up. Because they were actually in the process of discovering all of these during his lifetime. I mean, we were getting them one by one in the 1950s and 60s. So they said, okay, this is going to make a great big mess of the periodic table, so let's rip these things out and put them down the bottom. So the elements that follow lanthanum are called the lanthanides, and the ones that follow actinium are called the actinides. Okay, what are the three parts, three sections? Metals, nonmetals, metalloids. Metals, nonmetals, metalloids. Where are they located? Well, look. The gray is the metals, the yellow is the nonmetals, the blue is the metalloids. Now you'll notice a little oddball here. Hydrogen. Ever since you were a little kid, your mommy and daddy taught you the difference between metals and nonmetals. Right? So if you're in a crowd, you go, oh, metal, metal, nonmetal, nonmetal. And then you find hydrogen, you go, what is that? Is it a metal or a nonmetal? I don't know. Kind of looks like a nonmetal, but she's surely acting like a metal. What is it? Well, hydrogen is like that. Hydrogen looks like a nonmetal. It's a gas, but it also acts like a metal. So that's part of the reason why it's in that first column. Where are nonmetals found? Right side of the zigzag line. What are nonmetals like? Generally very different from the metals. Some are gases. One is a liquid, while metals are mostly solids, except for mercury. So basically, whatever metallic characteristics you have, non-metallic is going to be the opposite. Let's go over some of the metallic characteristics. Metals are good conductors of heat and electricity. Non-metals are not.
Good conductors.
Ever played with Play-Doh when you were a kid? Play-Doh? Allison, were you a Play-Doh girl?
Yeah.
Okay. Play-Doh is a good example of a malleable substance. If you can mold it into whatever you want, it is malleable. Ever played with Play-Doh where, was it you were making spaghetti or something? You pushed it through a hole and it came out like a tube on the other side, a wire? That is called ductile. Okay, so Play-Doh is malleable and ductile. Is it a metal? Well, can Play-Doh conduct electricity? No. Okay, is Play-Doh shiny or lustrous? No. Okay, so metals are shiny and lustrous. Non-metals are dull, dull. Instead of not, say dull. Metals will conduct electricity. Non-metals are non-conductive. Metals are malleable and ductile. Non-metals are brittle. Brittle. That's the opposite of malleable. Brittle. You take a hammer to a non-metal, and what do you get? A bunch of little pieces of non-metal. Yes, sir?
Whenever you said that, like, gases aren't, or the non-metals aren't conductive, I thought, doesn't neon, like, don't they, like, put electricity in it and it turns colors or something?
We'll talk about that. That's one of the things we'll talk about. Patience. But you'll have to get through the tough part of chemistry. That's your reward. Because then the fun part of chemistry begins next semester. Where are metalloids found? On either side of the zigzag line. On either side. They have characteristics of both. Actually, one of the greatest discoveries of the 20th century was when we realized that silicon could be made to conduct electricity. And whereas most things you would need to keep the wires separate, because whenever you conduct electricity through copper wire, it releases heat. And if you got too much of those copper wires conducting electricity at one time, you can build up a lot of heat. So they used to use vacuum tubes, these tubes where they had the wires in there, and there was a vacuum so that the heat wouldn't be conducted. Okay? So once we discovered that, we no longer used vacuum tubes. We started using little silicon wafers. And computers that could add, subtract, multiply, and divide went down from being 3 stories tall to something that you could fit in your wristwatch. I mean, it's pretty cool what Apple's going to do next year with the iPhone on your wristwatch. But if it wasn't for metalloids, that would not have happened. All right, so let's practice. Sasquatch, iodine, what family? Sasquatch. How many Sasquatches do we have here? Go, Sasquatch. It is a halogen. Very good. Magnesium. Magnesium. Alkali or alkaline? It's hard to tell the difference sometimes. Alkaline. Gold. Beth. Transition. Lithium. Salmon. Alkali. Very good. So, why is it that there are so few elements that are found in nature? Why can't we find just pure elements just sitting there? Because most elements, yes, Maxine.
Because they like to react with each other.
Yeah, they like to, he's right. Most elements like to react with each other. Okay, most elements like to form compounds. There are a few metals that are considered to be so ugly, so disgusting, that no one wants to mate with them. No one wants to react with them. They're disgusting. So we actually find them in nature by themselves, which is extremely rare. They are gold, silver, and platinum. Isn't that ironic? What we consider to be the most valuable metals on Earth, most non-metals would say, I would rather be alone than to bond with one of them. They are considered to be extraordinarily ugly. And yet we go around, oh, look at my gold medal, my gold ring, isn't it beautiful? And most of the oxygen around is going, ew, gross, why is she touching that thing? Think about it, not even oxygen will react with gold, and oxygen reacts with everyone. That ought to tell you right there. Okay, so what makes it valuable to us? It's not its prettiness, because it's considered to be ugly. Yes, Marie.
The fact that it doesn't react, so it won't change. So if you had a copper ring, it would eventually turn green.
Excellent. That's one good reason. The other one is, Max? They're rare. Anything that's rare, folks. If you had 1,000,000 Superman's #1 issue, what would it be worth? Nothing. Okay, but there's like 23 left on the earth. Okay? Now, what about football players? Should we be paying NFL football players millions of dollars? Okay, how rare is a player that can play at that caliber? Okay, so they're just like gold. They're rare, so they're worth more. How about teachers? How many teachers are there? Like millions. Why pay them anything? There's millions of them. I know. Look at this. Isn't this disgusting? It's platinum. Everyone say, ew. Platinum doesn't even react with anything. There are some non-metals that are also like, ew, no, don't react. Noble gases. I like to think of noble gases as kind of like the nuns of the element. It's like, okay, they're females, but no, you don't think of them in that way. Right? Noble gases, non-metals, they just don't react. They don't react. And, I have seen some beautiful nuns. You don't think of them in any way other than, yes, sister. Yes, sister. Okay? It is not done. All right? In the same way, noble gases are completely unreactive. Metals like to react with non-metals. Non-metals like to react with metals, except for the noble gases. Diatomic molecules are elements that usually given a choice, they'd rather just react with themselves. So they come in twosomes. They come in twosomes. So a lot of times we find them in the atmosphere as a twosome. They are very, very important to us, especially when we talk about chemical reactions. Okay? It is very important, and I mean very important, that you are able to recognize them as being one of these elements that come as a twosome. Okay, so here's an acronym to help you remember. Brother Huncliffe. Brother Huncliffe. Where the Br stands for bromine. The H stands for hydrogen, oxygen, nitrogen, chlorine, iodine, and fluorine. Okay, Grant back there he sat down and he said, I'm not going to memorize this. Even though, Mr. Moreno, you asked me not to memorize it, I'm not going to memorize it. Fine, Grant, look on the back of the periodic table. Just as long as you know where they can be located. Right in the middle. Do you see a little bit right of the middle?
Oh, I see it. I know.
On the back of the periodic table.
Atomic molecule.
Back!
Your best friend's butt.
Back! There! In the middle. Oh!
Harry's butt.
My best friend's butt is full of information. Hey, look. That's the periodic table.
No, is this like the front? Or
That's the front, and
the face?
all right. Here are noble gases. Notice the noble gases are singles. Okay, the diatomic molecules are couplets. Okay, we know what phase hydrogen and oxygen are. We're used to those. They're gases. What about fluorine? Pale yellow gas. Okay. Fluoride. There's a difference. And tomorrow I'll explain to you the difference.
It sounded the same.
No, it should sound the same. It's virtually the same thing. Okay. Chlorine, let me give you some advice that may save your life one of these days. If you see a colored gas, get away from that. There are no good colored gases. Okay? What? What did you say? Neon, in its natural state, is not a colored gas. Give it electricity and it will release light. But it's not a colored gas. Okay, if you see any yellow or green gases, get away. It's going to hurt you. Don't go, oh, pretty, and start sniffing it, because it'll probably be the last thing you sniff. Bromine is a bromine. If you can see the gas, get away from it, because really all your lungs are designed to do is breathe in air. That's right, non-colored gas. All right, brown liquid for bromine. Iodine is really weird. It almost looks metallic. It's shiny. Okay, I'll show you iodine next demo. Bromine, brown liquid. I love this picture. Okay, that is, I know it looks kind of yellowish. It should be green gas. This thing that looks kind of like robot poop, that's sodium. You could take your finger, which you don't want to because it'll react with the moisture in your finger. You could take your finger and push it down, and your finger would push down into that metal. Very soft. Let them react together, and you get salt. What? Because, I mean, you can touch it with gloves. You can with gloves, you can just touch it and mold it into little animals and stuff like that.
Wait, what is it called?
Sodium. Okay, keep in mind that, you know, it could explode in water, but, you know, it looks like a giraffe before it explodes. Okay, but isn't that crazy? These two things, when they react together, form A white solid that you put on your french fries. How many liquids are there at room temperature? Mercury, and each phase, each type of element has a liquid in its arsenal. Mercury for the metals, and for the non-metals, bromine. Okay, look back here. Let me show you how to cheat back here. Okay, if I ever ask, which I won't, what is the state of matter for silver? If it's black, it's solid. If it's red, it's gas, and there are two blues. Those are man-made. Man-made.
What if you can't see red?
Then whatever color you see there with nitrogen, oxygen, fluorine, that's the color for air, for gases. Okay, I've got one little bit to go. Some elements come in more than one form. That means it's the same thing, but it packs in together in a different way. So they actually appear to be different things when in reality they are the same thing. Examples of elements that come in more than one form are allotropes. 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 So if you come in various forms, you're the same element, but you come in various forms, you're an allotrope. The perfect example is carbon. Some of you are writing with an allotrope of carbon. What is it? Graphite. Now, it's called pencil lead, but pencil lead is a mixture of graphite and what else?
Red.
No. Lead is poisonous to us. Clay. And because I think at one time they used to have like little pieces of lead. They used to use little pieces of lead, and it's just the name stuck. Okay, so clay is what makes graphite harder. If you were writing with pure graphite, when you went to write, it would just ooze out of your pencil and smear the paper. Graphite is so soft that it's used as a lubricant. If you've ever...
Stuff that you put on those racing wheels and it makes it go faster?
Maybe. Is it like greasy feel? Black and a grease?
Yeah.
A shiny black and a greasy feel? That's graphite. They add clay in order to make it harder so that you can actually write with it. Actually, the more clay they add, the lighter the line they leave. That is why is anybody here in art class? Do you have a set of pencils? Are you in the art class where you have to... What?
The ebony pencil?
I don't know. But a number two pencil refers to how much clay is in the graphite. Okay? So a number 2 pencil will leave a certain darkness. Number 1 is even softer lead. So it'll make a darker color. Number 3, less graphite, more clay, so it's lighter. 4, lighter. 5, lighter. 6, lighter. So with every step, so people who are artists are going to want to use different pencils in order to show different gradients of depth. Yes?
Is 4 twice as light as 2?
I don't know if it's proportional like that. No idea. So, ladies, maybe one of these days, this guy that you've been dating for 2 years will come up to you. I mean, he is struggling he's still working through college, and so he gives you a ring with a little black chunk on it, a little piece of graphite. And he looks at you, Marieli, and says, "Oh dear Marieli, I know that this is not a diamond yet, but with the heat and pressure of my love for you, I know that I can convert this into a diamond real soon." What would you say? Would you say, "Nah, rejected"? It's the same thing, gang. It's the same thing. It's carbon. You realize that if you threw... Okay, girls, don't ever get PO'd at your boyfriend, your fiance, and take his ring and throw it into the fire. The gold will melt. The gold will be recovered. The diamond will burn just like any other hydrocarbon. It'll convert it straight to carbon dioxide. Your diamond will burn. It'll just burn.
At least sell it.
It'll burn and convert to carbon dioxide. So, don't ever throw an engagement ring into the fire. Just hold on to it, sell it. Okay, look at this. Here are the three forms. This three-dimensional object here, that's diamond. So if it forms these three-dimensional little tetragons, that's diamond. If it forms these sheets, these hexagonal sheets that slide past each other, that's why it's a lubricant. They slide. That's graphite. And this is about 20 years old. They discovered how to make this third allotrope. Folks, allotropes of carbon is changing science. Let me show you.
In this video, we are going to learn about the structures of buckyballs, also known as Buckminster fullerenes, graphene and nanotubes, and what their importance are in an area of science called nanoscience. You may already be familiar with diamond and graphite as two allotropes of carbon. Allotropes are structurally different forms of an element. There's a video on this channel called Giant Chemical Structures that you might want to look at. If you have watched this video, can you remember the structural arrangement of the carbon atoms in graphite? Pause the video and resume when ready. The answer is that graphite exists as sheets of carbon atoms arranged in hexagonal rings. Fullerenes are carbon-based molecules with a hollow cage-like structure. Robert Curl, Harold Kroto and Richard Smalley discovered the most common fullerene in 1985, the Buckminster fullerene. It consists of molecules containing 60 carbon atoms joined together, forming a hollow sphere. There is an alternating arrangement of hexagons and pentagons, much like that seen in a football. Can you think why the space inside the fullerene is of importance? Pause the video and continue when you have a suggestion. The answer is, the space is big enough for atoms and molecules to fit inside. Already, scientists are utilising this to cage radioactive metal atoms and drugs. In one potential drug therapy, buckyballs containing cancer drugs are coated with a chemical that causes them to gather around cancerous cells. Once there, they deliver their drugs without harming healthy cells. Graphene is very similar to graphite, except there are no intermolecular forces holding the hexagonal arrangements of carbon atoms together. It has a two-dimensional structure. It has some very special properties which make it a material for the future. Despite being one atom thick, it is incredibly strong. The graphene can conduct electricity as efficiently as copper. The graphene is virtually transparent, yet is so dense that not even helium atoms, which are tiny, can pass through. So far, we have encountered two examples which both share a common theme, the fullerene. Fullerenes hold a special importance in nanoscience, a relatively new area of science which involves the study of nanoparticles. Nanoparticles are tiny particles made up of only a few hundred atoms. They can measure between 1 nanometer and 100 nanometers across. A nanometer is a billionth of a meter. To illustrate how small this is, a human hair is about 100,000 nanometers in diameter. Fullerene particles can be joined together to make nanotubes. These nanotubes have massive surface areas compared to their volumes, and this makes them excellent catalysts. You may recall that a chemical reaction takes place at the surface of a catalyst, and so having more surfaces enables that catalyst to work more efficiently. Nanotubes are the strongest and stiffest materials ever discovered. Often they are used to reinforce tennis rackets made out of graphite. All of these fullerene structures are revolutionary in the developing field of nanoscience. The nanoparticles mentioned here could be implicated in the development of new self-cleaning coatings in ovens and on windows, new types of computer processing, very strong and light building materials, and these firings could be used as sensors to detect substances in tiny amounts, or to deliver drugs to specific sites in the body.
All right, I actually read just this past week that they've been dreaming of finding a way to build an elevator between the Earth and a station in orbit. And what they're thinking about doing is using these fullerenes, because they're super tough fibers that are very hard to cut. So if you made them thick enough, you could actually build an elevator from here to orbit.